very much for this introduction. So today I'm going to show you a computationally efficient approach for parameter estimation problem in finite dimension to generate sequences of transition probability density function between the prior PDF and the posterior PDF. So the selling point of this approach is that it allows you to perform an a priori estimate of the number of evaluation of the forward model. So let us start. So we are interested in inverting the parameter theta of dimension D, and for that we use the data y of dimension q, and we consider that y is y is the output of the forward model G polluted with a noise in this through this nonlinear function f. So typically f is covering additive measurement noise, multiplicative measurement noise, but also combination of those two and other type of noise. So for that we use the Bayes theorem here, so which tells us that we have the likelihood times the prior divided by the evidence. So the normalizing constant here is the P of y, is not known, and it is actually the bottleneck in the computational point of view, because it causes the majority of the challenging issue in approximating the posterior PDF or computing also statistics on the prior on the posterior PDF. So in the other end, we have the prior that is available to us and stand for our prior knowledge about the parameter theta. It is quite helpful to avoid rapid changes in the computation. We have also the likelihood function. That is actually where we confront the data to the model, and we consider this following general form of it, where the constant c is depending on the dimension of the parameter, but also on another parameter s that is standing that is quantifying the dispersion of the measurement error. So the misfit inside the exponential function is a quadratic distance that can be Wasserstein distance, total variation distance, L2 weighted distance, or also Hellinger distance. So in general, in real world application, G is quite expensive to approximate. So for instance, in geological science, it can be seismic waveform, it can be concentration fields in reactive flow, it can be space saturation in multi-phase flow. And starting from that, we consider a computationally intensive Bayesian inverse problem where almost the entire computational load is associated with the evaluation of the forward model G. So therefore, it is crucial to limit the number of evaluation of G. And one way of doing so, and maybe to further control the computational load, is to be able to perform an a priori estimate of the number of evaluation of G. So typically the challenging issue that we are addressing today are like, can we perform an a priori estimate of the number of evaluation of G? If so, then that will lead for sure to computational efficiency, computational scalability. And the other approach, and also the other point is that, can we track the flow of the update from the prior to the posterior? If so, then this is a good point to analyze the transport of the prior uncertainty to the posterior for the ill-posed problem, even in the nonlinear setting. So just to convince you more that the proposed method is really a breakthrough, let's see how the classical method of constructing posterior distribution behave in regard of those two statements. So first of all, we have importance sampling approach and associated. So where the main work is like how we can approximate the Bayes factor, and there where we applied a measure change here. So in that case, the construction of the importance distribution is actually the whole work, and one may need probably to do to run optimization just to find the maximum a posteriori estimate. So the second class of the method for inverse problem are the MCMC method. In that one, so the basic idea is to overpass the estimation of the bias factor and to use this proportionality relation to generate correlated sample. In that one also, the design of proposal distribution may be complicated. And we all know also that MCMC method require a large number of evaluation of the forward model. But also in top of all of those points, we have also the acceptance criteria that destroy completely the ability to count a priori the number of evaluation of the forward model. So we have also the third class of method for inverse problem that is optimal transportation. So in optimal transportation, mainly what you do is that you try to construct construct a map that is called push to forward map between your target distribution and your reference distribution by minimizing the transport cost function. So typically, just look at the target distribution, like your posterior distribution, and then the reference distribution will be your prior distribution or something built on the prior that is very easy to sample from, like Gaussian prior. In that case also, so the accurate evaluation of the transport cost in high dimension, it's very demanding. And also you may have cost of dimensionality in the optimization for the construction of T. Although you have two approaches of doing it, you can map via sample of the target distribution. In that case, you have to look to construct the inverse of T. In the other case, if you want to map via the evaluation of the target distribution, in that case you have to construct T itself. Okay, so in both of the three cases, you have either acceptance criteria to do, or you have optimization to run. So and those two things make you almost impossible to have an a priori estimate of the number of evaluation of G. So now let's see what power posteriori can give us in this setting. Okay. So the basic idea of power posteriori distribution is quite simple. Rewrite the Bayes rule here. Rewrite the Bayes rule with tampering the likelihood. So for alpha varying from 0 to 1, so your power posteriori distribution will be going from the prior to the posterior. So for alpha equals 0, you are exactly at the prior state. For alpha equal 1, you are at the posterior state. So the same dynamic is observed for the normalizing factor. So the normalizing factor is varying for alpha equals 0 from 1 to P of Y. Okay, so this approach has been around for a while, and it has different terminology depending on the community. So in molecular dynamic community, it is mostly called replica exchange method. In statistics and computational mathematics, so it is called parallel tampering. So here is a kind of chronological list of references where the main idea, I mean, the driving idea is the sampling construction. Instead of constructing the PDF itself, they are just constructing a sample. Okay, so here what we are going to propose today is that a different approach. We adopt like a different approach. We would like to construct the PDF, not the sample itself. Okay, so then we need first to characterize the power posteriori distribution using the Leibniz integral rule, and then also the only regularity of the continuity of the forward model with respect to the parameter of interest. We can show that that the power posteriori distribution is solved with this following partial integral differential equation with initial condition the prior. So actually, so you have equation where you have derivative and you have integral of the power posteriori distribution. Okay, and you can have you can see similar characterization in the studies from the University of Oxford, where instead to have alpha, you have a functional of alpha. Okay, and the expectation of the log likelihood with respect to the power posteriori distribution, it is known as the expected deviance. So here it can you can see from one that also it defines the direction to follow. For example, if you look at the guys inside the parentheses in equation 1, What that tell you is that this first term, the theta is sampled from the prior. In this one, you have to sample from the power posterior distribution. But then if this so then this one is almost constant, and this will define the sign. If the sign of all the guys inside the parenthesis is positive, it means that your power posterior distribution from one alpha to another one will increase. And then if the sign is negative, it means that it will decrease. Okay, so this is also the expected deviance. It is also well known in model selection, but our interest here are two. So the first of all, we are interested on the solvability. By solvability, we mean is this it is really meaningful to write one? Do we have solution of one? And then if you have solution of one, how can we write out the solution of one? Okay. So in the solution formulation, we have two approaches. We have the spectral formulation, but we have also the formulation that is based on the moment generating function. But in this talk, we will mainly focus on the moment generating approach. Okay. So for the solvability, we start by introducing new parameters. So we just drop the dependence on y. So you have the power posterior distribution, and this is actually the log. This is actually the log likelihood, and we see here that the theta is sampled from the prior, and we have this functional k of alpha and eta that will take the misfit inside the exponential, and the expected deviance can be written like this, and then we can rewrite completely the characterization equation in the following way. But here, if we look at this equation, what we have is that we have two problems. The first of all, we have this quantity that is on the diagonal subspace. That is one problem. And then the other problem is that we have this nonlinearity here. Okay, so we will try to drop first the nonlinearity, and then we will try to leave the diagonal subspace. So first of all, if we leave the diagonal subspace, we will go in the whole space. The difference between this one and this one is just that we replace eta by theta. So that means that we now extend the problem to the whole space. Okay, by now extending the problem to the whole space, this equation become a particular case of this one. So if we solve that this one have a unique solution, it means that this one also is having a unique solution. But another problem is that if we do this changing, is it really meaningful to write k of alpha, theta, and eta? Because we just change an argument. Is it really meaningful? So the point is the following: you look at the data space like a pseudo-Euclidean space, and then you see that this guy is actually a symmetric kernel, which is associated to the inner product, associated to the distance this that we give previously. Okay, so now to break now the nonlinearity, we introduce this form. So we said that the power posterior is the product of two functions, a function u and another function v. So and then we can write from our equation. So we can write this equation 2a and 2b. So we know that 2a have a unique solution, and we can write it out. But 2b, it is still a partial integral differential equation, but we change the kernel, and and we don't have now here any nonlinearity. So this equation is it's called Bayesian equation. So just for definition, Bayesian equation are class of equation in the form tree. So C, F, and the kernel K are given data of the problem. If you are really interested on Bayesian equation, there is actually very few work on this type of equation. So I really recommend you this book. It's very nice, and you will see a lot of application of the Bayesian equation for optimal control, and also for probability theory. So the main aspect with the Bayesian equation is that if you want to show the existence and uniqueness of solution, you have to write out the associate Cauchy operator, and to show that associate Cauchy operator is strongly continuous. That's the first thing. And the second thing, so you have to be clear that the space where your solution lives is a Banach space. So we are going to do that. First of all, we are going to give all the ingredients to define our Banach space. So we start by giving the space of the probability density function S. So, and then with this condition, we have that everything is bounded in this space. So we equip this space with the internal composition law, and also with this external composition law. So we can show it. We can show easily that S is the Banach space. So, but the problem here, we are not really interested on the space S, because our function is V. So then we have to define now a subspace SL where we have the log of the function is bounded. Okay, and this one is a Banach space also, because we are in finite dimensional first, and because also we get the completeness of this space just because of the concavity of the log function. So we have we construct the Banach space where our solution live. Now we will just need to extract the Cauchy operator. Once we extract the Cauchy operator, we have to show that the Cauchy operator is strongly continuous. So now for the Cauchy operator, we introduce this abstract function V in the same space. So, and then we rewrite our equation to be in the following form. So here, just to see that this derivative now it is in the Fraisier sense, right? So our Cauchy operator, if I can say so, it is given by this one. And the only things now is to show that this operator is strongly continuous. So that is quite easy. So you have just to consider a sequence of alpha n in the interval 0, 1 that converge to alpha, and then show that the sequence of the alpha of a of alpha n converge to a of alpha. Okay, and then by doing so, you saw already that this operator is strongly continuous, because because it is already bounded in this Banach space. Okay, so this is mainly the main line to show the solvability of equation 1. Now we are going to formulate a solution to our equation 1. So if you look at the equation 1, by just forgetting what is the integral sign, we can just look at it like a differential ordinary equation. By taking it like a differential equation or a differential ordinary equation, we can write it like this. Okay, so if you write it like this, we are not done yet, because what is inside we don't know. This one we don't know. The expected deviance, it is depending actually on the power posterior distribution. Now what we are going to do is to try to find a way to solve the expected deviance separately from this equation. Okay, and for that we will just introduce the log the moment of order n of the log likelihood with respect to the power posterior distribution, so which is here. And this function, this quantity is actually well defined, and it is even C infinity regularity with respect to alpha. So if it is C infinity regularity, we can do some differentiation, and after some differentiation we end up with this equation. So if you look at, well, the equation for what we have is that we have the moment at order n. It depends on the moment at order n plus 1 and the first order moment, and also at the moment at order n. So if we write it for n equal 1, n equal 2, and n equal 3, and up to infinity, we will have a kind of system of nested differential equation. Okay, so but if you want to get something from that, we cannot just we cannot just compute on this. We have to take the sum of it. And we have first to see if the sum exists, and then we take the sum, and then we work on that one. So to do so, we will just consider a positive real large enough, which is approximately 1. So we will see why we have to take it approximately 1 or smaller than 1. So and then after we do the multiplication with 4, and then we end up with this one, and then we sum up to infinity. By summing up to infinity, we end up with this equation. So this is actually the moment generating function of the log likelihood with respect to the power posterior distribution. Because we take the capital T beta almost equal to 1, this guys, it exists. You can show it. You have to play a little bit with Holder inequality and some feature of the measure itself, but with maybe one half of pace of math, you can show that this is well defined. Okay, and then the governing equation of the moment generating function is the following. So this is a first order. This is a first order reaction advection equation that have to be equipped with the initial condition. But we have 3 choices now for initial condition. We can decide to take the initial condition at alpha equals 0, or at alpha equal 1, or at beta equals 0. So if you look at the things at alpha equals 0, at alpha equal 1, we have to, it will require sampling from the posterior. But we want to have an a priori estimate of the number of evaluation of G. That means that we should not sample from the posterior. We have to restrict to all the sampling at the prior state. So this one we drop it. And then if you look at beta equals 0, that will give us the following initial condition, and then that will lead to a ill-post initial value problem, because we will have an infinity of solution. And then our choice will be then at alpha equals 0. Then we will take this equation with this equation and mix it with this initial condition, and then we can write out clearly the solution of the governing equation of the moment generating function using either characteristic method, or if you want also, you can just do it by change of variable. So we know now how to write the moment generating function. So now let's go to extract the first order moment in the moment generating function. We know that is the derivative of the moment generated function at beta equals 0. That is well known. That is that is a property of the moment generating function. And then by doing so, we end up with this integral equation. Okay, so if you are very good in solving numerically integral equation, you can just stop here and this is fine. But if you want to go a little bit further, we can see also that the moment generated, the expected deviance, it is solution of the Bernoulli differential equation of the second kind. So with that, so we can rewrite now our solution formulation, saying that the power posterior distribution exists and it is given by this formula, and then the expected deviance here, it's also given by this. So we can compute the power posterior distribution at any alpha without sampling, without doing any extra sampling at that position of the alpha. So all the sampling are restricted at the prior prior state. So now let's see what we have in the numerical results. So we do some conceptual check in the numerical result section, just to see how this method behave in front of non-Gaussian error, and also how it perform in inverting multimodal parameter. So first of all, before we will see why it is important to keep the logarithmic scale of the thermodynamic identity. So if you look at, well, the expected deviance is something like this. So you can decide to say, oh, okay, why can I not, why I cannot just take the expectation with theta of the pi of theta y alpha and then log of pi of y theta. But if you do so, you will leave this log scale. And then if you leave this log scale, you will probably maybe in this zone, and then you will have this numerical underflow. But then in our cases, we did not stay in this line, in the log scale. We leave little bit the log scale by exploring this area. So we are still safe. We are not in the instable zone. Okay, so this is very important to keep the stability in the numerical computation. So now let's see the algorithm. So what we need to give to what we need to give as an input are the data, the forward model, and then the template grid point. So we generate n samples from the prior, and all the evaluation of the G are restricted at the step 2. After the step 2, so everything is just a numerical operation. So you can see here that this pseudocode is easily scalable. So the first example is very simple, is a well-posed linear with Gaussian noise. We just wanted to see how the expected deviance behave from the prior to the posterior. So we can compute clearly the expected deviance in this case, and we see here how the uncertainty shrink from the prior here to the posterior here. Okay, but this is a well-posed problem. Think now if you have ill-posed problem. Will we have the same behavior of the flow, or the behavior will change, or should that can help us how to parameterize better our prior distribution. And here we just plot the computational bias and the statistical error. What we can see here is that this we reduce drastically the statistical error of the expected deviance from the prior here to the posterior here. So we see that we could control it of order 3 in log scale. So now the second example is we want to confront now this approach to the non-Gaussian error. So we picked this example from the paper by Motame and Appel in 2019. So it's a 1D wave equation with initial pulse of this form, and the parameter of interest is the position and the amplitude of the wave. Okay, so and the forward model is known. So even though the problem is governed by a partial differential equation, we know the exact solution. So there will not be there is no any error from the discretization, and we have 7 receivers that collect the data, and the data is parameterized as the following. So we have here a Pigel noise, which is a multiplicative noise, and then plus a uniform noise here. And this is how the waveform looks like at the 7 receivers. And here we write out the likelihood. We see here this is our constant that we define at the maybe at page 2 or 3. So it depends on D and also on S. Okay, so what we show here excuse me, what we saw here is like how the power posterior distribution changing for different alpha. So we have here the plot for alpha equals 0.01, alpha equals 0.2 up to alpha equal 1. The third example is multimodal inversion. So we consider also very easy, very simple problem, y equal theta plus epsilon. But the thing is that now here we suppose that the data are from a categorical distribution of M mod. So which means that we sample data from the Gaussian around theta t and sigma square, where theta t can be any of those values. Okay, and then the likelihood writing is little bit different, because we have to we can put some weight in some of the mode if we want. So this example we constructed based on the following paper and also in this PhD thesis. So this is the moment generating surface for alpha between 0 and 1, and for beta between 0 and 1. Now, if we consider that we have only 3 modes in the data, and that the mode are a little bit weighted. So the first mode is having the weight of 0.3. The second one is the one that is the most important, and then the third one is 0.2. So we see that we know that, for example, if you are having multimodal, if you are doing multimodal inversion, you depending on your data set, on the size of your data set, you can invert to some, you can invert to some or all of the points. So here we have only 3, so we can see that we can see the evolution of the power posterior distribution with respect to alpha, but also we can see also how it changed with respect to the data size. And here we add all the 20 modes. So we have 20 modes, and we are changing alpha from 0 to let's say very close to 0 actually, to alpha equal 1. And here we just increase the number of the number of the data. We can see, for example, from this line, from this line, so the number of data equal 10. So we don't have all the modes. So this is because that you need more and more data to get all the modes. And just to conclude, so we presented something with which is quite useful if you want to restrict all the evaluation of the forward model at the prior state, and that will allow you to perform a priori estimate of the number of evaluation of G, so which will lead you to computational efficiency and for sure to computational scalability as well. But also it open access that we can look now the flow of the prior uncertainty in ill-posed problem. For example, in this presentation, example 1 is a well-posed problem. But think if, for example, the Q, the size of the data, and D, the size of the parameter of interest are different. In that case, what we will see. So we are actually working on that. So we are actually also trying to use the MLMC approach that to get more accuracy for the estimation of the expected deviance. So I would like to thank Raul and on his feedback for the earlier version of this work, and also Jesper for the long discussion. Thank also to Youssef Marzouk and to Cody for the discussion, especially on the spectral approach. So the talk was mainly based on this paper that you can find in archive. So thank you all also for your kind attention. Thank you very much.